Oh, much better. Okay, so derivatives of exponential functions. All right, let's sketch the graph of e to the x. Yeah, y'all know what e to the x looks like, right? Parent function, exponential. Yeah, it has a horizontal asymptote on the x-axis. But the nice thing about exponentials is the graph is only affected by the horizontal asymptote on one side. So in this case, we got f of x. And what's the y-intercept? How could you figure that out? E to the 0 is 1. Okay, let me make the horizontal asymptote a little more pronounced. Now this is your parent function. Okay, it increases at an increasing rate, and in this case, e is going to be the most common irrational number that we're going to see from here on out. Pi is pretty popular in geometry, right? 3.14159, blah blah. But e in calculus and analysis, e reigns supreme. Okay, it's do your math homework. It's called a transcendental irrational number, as opposed to an algebraic transcendental number. Numbers like e and pi are never going to be solutions to algebraic polynomial equations, whereas like the square root of 2, for which Hypasus lost his life, square root of 3, cube root of 5, bless you, all those are algebraic irrational numbers. All right, and we did have the math club presentation on e, how it showed up in nature, so y'all are somewhat familiar with that. We're going to go ahead now and we're going to sketch the graph of the derivative on the same coordinate plane. So I'm going to pick blue for the derivative. Now here's how we do it. We analyze the slopes of this graph at different values of x. And at those values of x on the same graph, we're going to plot the y value of what we think the slope is. Okay, so I'm just going to kind of draw a tangent line. And we're going to be able to move that. This is kind of nice with notability that we can do that. So give yourself a long handle. Is that good enough? Let me do it like this. Hang on. We want a long handle because I got big fingers. Okay, so I moved the E. No. There we go. All right, so here it is. No, maybe a smaller handle. Not as easy as it looks. Easy. Okay, right there. Right there. That'll be good. Right there. Okay, so at that value of x where it's tangent, what would be an approximation of that slope right there? Just a ballpark figure. 1/2? Yeah, it's definitely less than 1. It's less than 45. So 1/2 might be somewhere right in here. Okay, good. Let's move it over now. Let's move to the right a little bit. How about right there? Right there. We're right here. It's tangent right there. What would be that slope? Bigger, huh? 3/4, maybe. It's certainly bigger than this one here, right? So I'll put it right there. Okay. Let's move it right there. At that value of x where it's tangent, the approximate slope is, I don't know, 1, 2, right? Bigger, yes? Correct. Thank you. Okay. And then I'm going to I'll go one more time. If I can. Dumb fingers. I even washed them. That's good interlude music. Okay. How about right there? How about there? It's tangent to the curve way up there. So what's 7? Okay, I like that. So at this value of x right up here where it meets, it's 7. Okay. Now let's work back the other way because I'm so good at going to the right. Let's see if we go back to the left. We said that one was like 1/2 right there. Yes. If I keep going back to the left, right there, what would be the approximate slope right there? 1/4, right? Now it's less than what it was at 1/2. So somewhere right in there. And I'm not going to do it anymore because my fingers appear to be broken. But as I continue to go backwards to the left, what are my slopes approaching? 0, because the tangent line is approaching horizontal. So if I were to then get rid of this little line and whatever I was carrying around with it, right? The of x, right? I'll put it back. And I were to connect the dots, it might look something like this. This might be what the graph of f prime looks like. Correct? Yeah. So not only on the graph of e to the x do the y values increase at an increasing rate coming from 0, but its derivative qualitatively, that's all we did here, qualitatively appears to kind of have the same shape, right? So guess what type of function the derivative of e to the x is going to end up being? E to the x is an exponential function. How do we know e to the x is an exponential function? I skipped right over that. Yeah, the variable is in the exponent, right? Yeah, yeah. So you have a numeric base and a variable exponent. That's how you can tell. Sorry, I should have done that first. A little bit distracted today. Number in the bottom, variable in the top. If it were switched around like x to the eth power, that would be more like a power function, like x squared, x to the 1/2. So this is an exponential function. It would appear that the derivative then of e to the x is another exponential function. What would be the equation of it? Well, that's a little bit harder to tell qualitatively. So here's what I want to do. Since y'all are pros now at the calculator, because calculator dude, because y'all did this with Miss Skurhawk yesterday, I'm just going to go to y equals, and in y1, I'm going to graph e to the x. Now, on the home screen, there's 2 places to get e to, oh, by the way, does anyone in here have one of my yellow calculators? Do you have number 1? Okay, good, good, good. It was missing, and I was like, oh no. Okay, okay. All right. All right, that's good. As long as I know where it's at. I know where it's at. No, you can run it out. That's fine. I just now that I know where it's at, it's good. Okay. All right. No, you're good. You can either go second ln and it goes e caret. It automatically puts you in exponent land. Or if you want to do the exponent yourself, you're like, I don't need no stupid help from you. I can do my own caret calculator. You can also get e the number by hitting second division. That's how popular e is. He shows up twice on your calculator's home screen. Now, if you go second division instead of second ln, you got to do your own caret. All right, there's e to the x. Let's go ahead and set up the window. I just want to graph e to the x. Go to the window. And let's see, our graph here goes from, let's go from -3 to 3. And then we don't really need to see below the x-axis. So let's just set that like at -0.1. I do want to see the x-axis. And then up to 10, yeah, that might be good. And then we'll just leave our x scale, y scale at 1. That doesn't really matter. You can turn it off to 0 as well. All right, hit graph. Come on, e to the x. Whoa, there he goes. Not bad, not bad. Pretty good window. Okay, now go back to y equals, go down to y2, and we know how to graph the derivative of a function without knowing its equation. But before we do that, click to the left of y2. Y'all have color calculators, you could do this too. Hit enter. In black and white, it gives you a thicker line quality, so you can actually see it. Now let's graph the derivative. Math 8, derivative with respect to x of alpha trace number 1. And we'll graph it by doing it with respect to x. All right, so that's how you get the calculator to graph the derivative. Now it's going to do it quantitatively because remember, it's computing slopes at each point and plotting numbers. We just did it qualitatively. Here we go. I just went like -3 to 3 and then -0.1 to 10. Yeah. Oh, look at that. Look at that. See it? Oh, look at that. Look at that. Now it looks like it traced over the top. Go to your table. Your table is under second graph. And now you can compare the columns of the function and its derivative. They look pretty similar, don't they? Okay. Now, if you ever want to see more decimals, scroll over to the column and it'll expand it on the bottom. And you notice they do differ somewhere deep down the line, right? That's just because your calculator is truncating. That's rounding error. So in this case, it's almost better just to view it in the truncated columns. What do you notice about all these y values all the way down? They're the same, aren't they? They're the same. So that is proof by TI-84. That's what we call that. That blue graph that I drew is actually inaccurate. It should have been drawn directly on the top. Okay. So here's the big reveal. You ready? The derivative of e to the x is e to the x. He is his own grandpa. Hey, guess what the antiderivative of e to the x is? E to the x. If you're your own grandpa, you are your own grandson. So C, right? Yeah, I didn't want to bring that up, but you're right. Yeah, very good, very good. So it could be, well, it could be e to the x plus c. All right. So in this case, E, which actually stands for Leonard Euler, right? He's a Swiss mathematician. That's how you spell Euler in Switzerland. Okay, Leonard Euler. People see that and they go Euler, but he was the guy that kind of discovered E and used E, and so it was named after him. But you know, in all humbleness, lowercase e, not capital E, because big E is energy, right? Einstein's energy. So Leonard Euler, in mathematics, Euler is king. They say he has more original publications than any other person who ever lived. Paul Erdish has more papers, but he collaborated more. And Paul Erdish is another one that starts with E. And here's how you spell his name. If you saw that, would you think, oh, Erdish? Erdos, right? But it's Erdish. Erdish. Paul Erdish and Leonard Euler. Those are the two most prolific mathematicians in the whole world. Okay. Oh, he does everything. You know, have you heard the game 7 Degrees of Kevin Bacon? No. Have you heard 7 Degrees of Separation? 7 degrees of separation is supposedly that every single human being is within 7 links with everybody else. No, they turned that into a game called 7 Degrees of Kevin Bacon, where you mention 2 random actors or actresses, and the goal is within what did I say, 6 degrees, 7 degrees. You can relate them to each other by way of movies, common movies. Like he was in a movie with so and so, who was in a media with. Oh, is it?
You can make it Wikipedia because it's like, you know, they have like little.
Oh, do they? Yeah.
So you can do that too.
Well, they have something called an Erdish number because he's a modern mathematician. An Erdish number is basically how closely you were to publishing a paper with Paul Erdish. Okay, so if your Erdish number is 1, you published with Paul Erdish. If your Erdish number is 2, you published a paper with someone who published a paper with Paul Erdish. Yeah. And he was again, you can look him up. He's a modern mathematician. He lived very humbly. He just traveled from university to university and relied on handouts to feed himself and to live. You know, but just crazy brilliant minds.
Oh, he's got 2 little dashes over.
Yeah, it's yeah, I guess. Okay, so that's how we know it's Erdish. I guess it's an umlaut, but it's not a German umlaut. I don't think.
No, it's like 2 little dashes.
Yeah. Okay. Anyway, that's what E is for. Now, how often are we just going to see the derivative of e to the x? Well, maybe a lot, but not always, because the chain rule is always in the house. So here's the same rule, but with the chain rule built in. This is the chain rule built in. So if it's ever e to the blob, where the blob is something more than plain old x, in this case, call it u, the derivative of e to the blob is going to be e to the blob itself, and then times the chain rule, the derivative of the blob, right? I don't even have to mention that because you know the chain rule, but because it's a new rule, I throw the chain rule in there. And that's probably something more likely that we're going to see, okay? All right, let's try it. Well, bless you. Here it is. Example 2. Find dy dx if y equals, bless you, e to the quantity x plus x squared. So this is exponential, yes? How do we know it's exponential? X is in the exponent. Good. That's how we know. So here's what people who don't first size it up and realize it's exponential, they go, oh, I know the power rule. X plus x squared times e to the x plus x squared minus 1th power. Multiply and subtract, right, everybody? Right? Multiply and subtract. That's not right. And then, of course, times the chain rule. No, that's the power rule. The power rule only works when it's x to the number power. When it's number to the x power, that doesn't work. Okay, so what is it? Well, it is going to be itself. The derivative of e to the blob is e to the blob times the derivative of the blob, which is 1 plus 2x, parentheses. Okay, that's the answer. So size up your problem first each and every time. Is it a power function, variable to a number, or is it exponential, number to a variable? If it's number to a variable, especially if it's e itself times the chain rule. And that's it, you're done. You can bring the 1 plus 2x in the front. All right, now, are there other bases out there? Yes, yes. So let's look at 2 to the x. If I were to like try to qualitatively get the graph of the derivative of 2 to the x, well, my first step would be the same, right? Y equals 2 to the x power. If I was to qualitatively come up with the derivative for that, it would kind of be the same that I did for e to the x, right? It would be exactly the same analysis. So could it be that 2 to the x is also its own derivative? I don't know. What about 5 to the x? Could it be that 5 to the x is its own derivative? Well, if you graph the derivative of both of these, I'm not going to do it. You're going to see that one of them ends up being steeper. The 2 to the x ends up being less steep, and the 5 to the x ends up being steeper. Okay, but they do both end up being exponential. So how do we vertically stretch or compress a function? We multiply in the front by something, right? In the standard transformation form, A, B, C, D, the A is the vertical stretch or compression. They're both going to pass through the point 0, 1. And normally I would do this with the calculator to show you, but you could just take my word for it, okay? The derivative of 2 to the x is the flatter one, and the derivative of 5 to the x is exponential, but a little bit steeper. So here's what I do know. I know the derivative with respect to x of 2 to the x is going to be some a times 2 to the x. And because it's flatter, I know that a has to be, the absolute value of a has to be less than 1, right? Between 0 and 1. Like 1/2, right? Half as tall, vertical compression. And then same thing for this one, 5 to the x. It's going to be some vertical compression times 5 to the x, except now it's going to be greater than 1, like a 3 or a 5, okay? And we could probably guess and do trial and error and sneak up on it. But you know what? We're going to do better than that. We're going to derive it. We're going to derive it, okay? So let me show you how we're going to do that. To derive it, we're going to need to review a couple of things from pre-calculus, okay? Namely this, e to the natural log of x equals x, which equals the natural log of e to the x, okay? This is really piggybacking on the previous section, because how are e and natural log related? They're inverses. And what happens when you compose two inverses back to back in either order? Yeah, they equal x. They undo each other, right? So we start with x on the left, we natural log it, and then we e it, and we're back where we started at x. On the right side, we start with x and we e it first, and then we natural log it. Okay, but this is a really common identity now that we can use. So watch this. If I can write 2 to the x as a power of e to the x, I think I can use the rule that I've already learned about e to the x. Well, I can do that, right? 2 to the x is the same as e to the natural log of 2 to the x, I believe, right? Verify that for me. Look up here. Look at this left one. E to the natural log of blob should equal the blob, right? So look what I wrote. I wrote e to the natural log of the blob, which is 2 to the x. It should equal 2 to the x. Yeah, so that is correct. Now there's another thing that we have to review. This, okay? The natural log of x to the nth power is the same as n times the natural log of x. Logs make molehills out of mountains, okay? They turn exponentiation into multiplication. You could bring that exponent out front. So look what I can do now. In the exponent, I could bring that x out front here. So now it's e to the x times the natural log of 2. Verdad? See? And now by the commutative property, I'm going to rewrite that in the top as the natural log of 2 times x. Why did I put the natural log of 2 in parentheses? Because it's a number, right? And if I just put natural log of 2x, you might think the argument is 2x. It's just a number, natural log of 2 times x. Now I know how to take the derivative. Watch. The derivative then with respect to x of e to the natural log of 2 times x is, using the e rule, what's the derivative of e to the blob? E to the blob times the chain rule, the derivative of the blob. What's the derivative of the natural log of 2 times x? Well, if natural log of 2 were 5, what would be the derivative of 5x? 5. Yeah, what's the derivative of 3x? 3. What's the derivative of a number times x? That number. So it's just the natural log of 2. Okay, again, notice this is not the natural log of 2x. That's not what we're talking about. We're talking about the natural log of 2, the number, times x to the first power. It's linear. Well, my goodness. If that's the answer, then let me get this back into its original form. What's another name for e to the natural log of 2 times x? Well, it's equal to what? All the way back over here. 2 to the power of x. So 2 to the x times the natural log of 2. Well, again, I can write that in front to make it an a value. And the natural log of 2 is about 0.0693. Which is less than 1. So there you go. What's the derivative of 2 to the x? Well, it's 2 to the x, just like e to the x, but now times the natural log of 2. What do you think the derivative with respect to x then of 5 to the x is? 5 to the x times the natural log of 5. You're right. And the natural log of 5 is greater than 1. What would be the derivative of the natural log of 1/2 to the x power? 1/2 to the x times the natural log of 1/2. Well, shouldn't that work for e as well? Yeah, what would be the derivative using this new pattern with respect to of e to the x? Well, it should be e to the x times the natural log of e. But what's the natural log of e equal to? It's equal to 1. And what's 1 times anything? Itself. So guess what the only exponential function is who's its own grandpa? E to the x is the only exponential function that is entirely, exclusively its own derivative. All the other exponential functions are dilations, vertical dilations or compressions of themselves, okay? By a scale factor that's always the natural log of the base. See, we made some good progress today in more ways than one.